So we have a curve and we're told there's only one stationary point between 0 and pi. So on our diagram we see, oh, look, there's a stationary point and it's marked with A. So A is the x value and it tells us that. Then it tells us, all right, show that the tan of this x value, A, is equal to negative a half of the x value, which is A. Right, so to do this, we're going to have to find that x value. We're going to find the value of A. And how do we do that? We're going to do the derivative of the function. And when is the derivative equal to 0? And what is that value? So let's get to work. To find the derivative, we have got the product rule, because we've got a function times a function. Actually, it'll be easier if we write this first a little differently. So let's write it as sine of x to the half, and that may help us with the derivative, which is then going to make equal to 0, so we can find A. So dy dx. Using the product rule, we differentiate the first function, which is x, and we get 1. We leave the second function the same, and we have sine x to the half, which is a square root of sine x, of course. And then we're going to add. We leave the first function the same. We differentiate the second function. So now we have to use the chain rule. The half comes out the front. These are all multiplied, by the way. And then we're going to differentiate sine x. We differentiate what's inside the brackets. We get cos x. We leave the brackets the same, sine x, and we subtract 1 from the power, and we get negative a half. That is our derivative. Okay, we're trying to make that 0 to find the stationary point, right? We know there's only one between 0 and pi. All right, so to make that 0, we're going to have to turn it into a single fraction. And let's see what we've got here. So we've got the square root of sine x plus, we have x cos x divided by 2 root sine x. All right, perfect. So sine x to the negative half means it goes to the bottom of the fraction and becomes positive a half, and a half is the square root. And 2 is already on the denominator, so we have 2 root sine x on the denominator, and x cos x stay on the numerator. So to turn our other fraction to the same denominator, which is 2 root sine x, we have to multiply sine x by 2 root sine x. Root sine x times root sine x is just going to become sine x. It gets rid of the square root sign. So we have 2 sine x plus x cos x over 2 root sine x. All right, that's helpful for us because for the dy dx to be 0, when dy dx equals 0 in a single fraction, that means the numerator is 0. So we have 2 sine x plus x cos x, well, cos x equals 0. Okay, I'm going to pivot at this point and say, we know the x value where the gradient is 0, there's only one stationary point, is A. So I'm going to replace x with A and get 2 sine A, because it looks like this is going to turn into what we want. And here we have a cos of A equals 0. Okay, how is it going to turn into what we want? Let's take the A cos A over to the other side and get 2 sine A is equal to negative A cos A. Let's divide both sides by cos A, and we'll get 2 sine divided by cos. Sine of the angle divided by cos of the same angle is tan of the angle, and that is negative A. Let's divide both sides by 2, and we'll get tan of A is equal to what they asked us, negative a half of A. That's what we had to show. Right, moving on then, we get to verify by calculation that A lies between 2 and 2.5. Right, so we'll grab the equation that we have, and we can rearrange that into tan of A plus a half of A. What are we going to do? Let's call it the function of A is equal to that. So what we know is this. That was when the derivative was 0. or the gradient of the curve is 0, this is the solution. And so that equals 0. Right, so if we add a half of a to both sides, we'll get 10a plus a half of a equals 0. Now we want to say that, oh, well, what's the root of this function? That is the root of this function. A root of a function is where the function equals 0. And so let's verify that it lies between 2 and 2.5. All we have to do is put 2 and 2.5 into the function. So we're going to get 10 of 2 plus a half of 2. Now remember that we are differentiating and integrating. So whenever we use trig functions, we have to use radians. Put your calculator into radians to solve this. When we put that into our calculator, we get the answer is negative 1.185, which is great. So then we do the other number, which is the function of 2.5. In other words, we're going to make a 2.5. So now we're looking for the tan of 2.5 plus half times 2.5, and we put that in our calc, and we will get 0.503 approximately. We're rounded. We rounded both of those, so we should put an approximate sign there. All right, so what that tells us is the root of the function, or when 10a equals negative half of a, is between those two values, because one is below the axis and one is above the axis. So as we should definitely write something to state what has happened here. As one solution is negative and the other positive. A little more space, please. Oh, the root of the equation is between 2 and 2.5. All right, that's great for us. All right, so for part C, we have to show that if a sequence of values in the interval 0 to pi given by an iterative formula of something, xn is pi minus inverse tan of a half of xn, converges, then it converges to the root of the equation in part A. Well, this is the equation from part A, which we were trying to iterate to the root. If we were to iterate this to the root, we would rearrange this so that a is equal to, and the negative half, take it over and get negative 2 times tan of a. And then we try and use an iterative formula to converge that. What you should notice there, though, is that the a on the left would be the next a that we would use, and this a would be the current a. So we put the current a in to the tan and see what you get, and you go to the next a and then use that again. And so that's effectively xn plus 1 is equal to negative 2 times tan of x. Right, so that is an iterative formula from part A. We're going to try and take what they've given us and see if it converges the same as that. So instead of xn plus 1 and xn, as we know, when we do the iterative process, we would introduce those concepts into the term. We can just write what they gave us as x is equal to pi minus the inverse tan of x on 2. All right. That inverse tan is somewhat problematic. Let's try and get rid of it. Let's take the inverse tan over to the other side, add it to the x, and take the x over and subtract it, and we will get the inverse tan of x on 2 is equal to pi minus x. So just a little rearranging. Now we can say, oh, inverse tan, we know how to unwrap that. X on 2 is actually going to equal the tan of pi minus x. Okay, that actually looks pretty close to what we have. Let's expand the tan pi minus x. You might remember that we used earlier today the tan of a, this is from the formula sheet, minus b is equal to the tan of a minus the tan of b divided by 1 plus tan a tan b. This is going to be quite good for us because we should know the tan of pi is 0. Tan of 0 is 0 and tan of pi is 0. So this becomes the tan of pi minus the tan of x divided by 1 plus tan of pi times the tan of x. Okay, so tan of pi is 0, so we just end up with negative tan x over 1 because tan of pi times tan x becomes 0, so you have 1 plus 0 on the bottom, and you only have negative tan x on the top, so we end up with negative tan of x, and that's x on 2. So we can take the 2 over, and we'll get x is negative 2 tan of x, which is exactly how we would make the iterative formula. Let's make it look like what we started with. That tells us that the tan of x is equal to x on negative 2 or negative a half of x. All right, so if it is going to converge, it will converge to A because it is the same equation as what converges to A. Okay, on to part D. Use the iterative formula given in C to determine A correct to 2 decimal places. Give the result of each iteration to 4 decimal places. Right, well, here's the formula given in part C. So the good news is, even if you don't work out part C, you should be able to get part D by just using the formula. So we know it's somewhere between 2 and 2.5, so we should start our x value, let's say x1, somewhere between 2 and 2.5. Let's start at 2.25, because that's halfway between. Seems like a good place to start. Remember, our calculator should be in radians mode, and all we do is now just enter the previous value in and find out what the next value is. And when we do that, we're going to get 2.2974. 2974. That's actually close to 2.25. We have to read the question, we have to give each iteration to 4 decimal places, so that's good. And we just do it again, and we'll get the next iteration, and in this case it's 2.2871. They don't go to the same value when you round to 2 decimal places, so we keep going, and we get the next iteration is 2.2893. All right, so right here, you should note that if you round the x3 amount to 2 decimal places, you get 2.29. And if you round the x4 to 2 decimal places, you get 2.29, which is the same value. So we could technically just stop there and say, we're close enough. But if you wanted to be really sure, you can grab another value, and we would get 2.2888. 2.2888. Now remember, because the iteration is going down, it's going lower and then higher. So from 2.25 to 2.29, it went higher, and then to 2.28, it went lower, and then to 2.289, it actually went higher again, and then to 2.288, it went lower again. Every time you do the 2 iterations, the answer is somewhere between those 2. And if 2 consecutive iterations round to the same value, well, that is the answer to this number of decimal places that you want it to go to. So we could have stopped earlier, but if you round x4 to 2 decimal places, you get 2.29, and if you round x5 to 2 decimal places, you get 2.29. All right, so we have an answer. Therefore, the answer for A, because we have to determine A, it says in the question, A is equal to approximately 2.29, and that's to 2 decimal places, and each iteration was to 4.